All right, let's go ahead and get started. Good morning, everyone. Feels kind of like fall out there. So, lab this week, I already mentioned it, but you're going to be doing coordinate system work. You will be correcting some on-the-fly projection problems when ArcGIS Pro doesn't know exactly how to deal with coordinate transformations, right? So if you think about your view of a map, it's always projected. Your computer monitor is two-dimensional. You're mapping three-dimensional things. So there's always a projection that's being performed to create a map. Typically, the default is something like WGS 84, which is kind of similar to a Mercator projection as it's viewed on the screen. But yeah, you're going to be working with these coordinate transformations, dealing with some detailed maps of parcels, and fixing some problems with the automatic conversions between coordinate systems. If your lab asks you for cartographic elements, we've sort of been removing a lot of this from the labs over the past few years, but I do want to just mention this so you know exactly what I'm talking about when your lab asks for this. And some of these can be dropped depending on the circumstances, right? We talked about map conventions and how, especially if north is up, a general audience reading a map won't have too much of a problem with that. But the cartographic elements sort of that are default are a data frame or a neat line, kind of a box around your map to separate it from the other elements on the map, like the title, the legend, perhaps, unless you put your legend on the map itself. Typically, you might as well just put a north arrow, unless it's really getting in the way. Scale bar is always useful. And I also like to add some text with the representative fraction scale. If you're using any data that needs a citation, you should add that with some text. You'll notice that a lot of the vector base maps that are included with ArcGIS are actually automatically included as text on your maps. There's a trick to getting rid of that text. I'll show you. I can't do it on this computer actually because I don't have desktop installed here. But next time I'm running my laptop, I'll show you the trick for getting rid of that or placing that text somewhere else. And then finally, always remember to include your name and the date. All right, so last time we talked about coordinates. Today, the focus of the lecture is going to be on projections, how we transform our geographic coordinates on a spheroid or an ellipsoid to our flat plane representations of the Earth. Couple examples here. World Mercator, very common map projection. We've talked a little bit about how it really drastically increases the size of features towards the poles. And that's because this is a cylindrical projection. So we'll talk more about what a cylindrical projection means in today's lecture. Another example of a very different projection is an azimuthal equidistant projection. One thing I want to highlight is you can really infer a lot about the projection based on its name. So azimuthal means that it's a flat plane. We've intersected that flat plane with the Earth at one point. In this case, that point is the North Pole. And then we're projecting the Earth onto that flat plane. And the way that we're doing that projection preserves distance from the center of the map to all other locations. So this one is equidistant map, not necessarily an equal area map. All right, so there is a lot of information in the world of map projections. The basic thing to remember is that the projection process affects shape, area, direction, and or distance. And typically what you can do is you can perfectly preserve one of these properties at the sacrifice of the other three. And then there are projections that are compromise projections that try to minimize distortion in all four of these areas, but no map can do a perfect job of preserving all of these projection properties. So you'll find projections that focus on shape. You'll find other projections that focus on area, etc. So this kind of funky map projection you see on the right here, it's kind of a nerdy thing in the world of cartography. People kind of compete to have the best compromise projection, like how close can I get to preserving all of these properties? This is one of those examples. It's called Fuller's Dymaxion. And the choice the cartographer made here was, of course, having to split up the map in the oceans. So it really focuses on the continents, makes sense for human applications. Direction is, of course, kind of a problem, right? North is kind of to the left on the right side of the map, and north is to the right on the left side of the map. So direction is definitely compromised with this map projection. Although direction is preserved from the North Pole to all other locations on the Earth. And it does a pretty good job with shape and area throughout that map projection. Before I get into the details of more map projections, why we might choose one over the other, I wanted to highlight or revisit an idea that I talked about in last lecture, which is the shortest line path between 2 points on Earth. And I want to illustrate how different projection choices can represent different paths in different ways. So I mentioned this idea of great circles. These are lines that are defined by planes that pass through the center of Earth's mass. So you can imagine this curved line down here, this great circle path, as being the product of a plane that passes through the center of the Earth, intersecting with the Earth's surface. And this would actually be the fastest way to travel between Seattle and London because of the three-dimensional nature of the globe. So going up close to the Arctic Circle, crossing the southern tip of Greenland, near Iceland, and then descending down into London. The reason Great Circle routes took a long time to be adopted by navigators is because they were difficult to navigate these paths, right? Especially prior to the advent of GPS. Because you have to start out heading northeast, then you're heading due east, then you're heading southeast. And to effectively navigate with a compass, you need to know exactly how far you travel. So for early navigators crossing oceans, that was really difficult to do. So instead, they would just follow what's called a rhumb line, or a line of constant compass bearing, which was not the most direct path. So on a Mercator projection, which was our early example of a map developed for navigation, rhumb lines appear to be straight, which makes it really useful for just navigating using a constant compass bearing. But on a newer map with a mnemonic projection, this projection makes all great circles straight lines. We can see how our shortest distance path is actually a straight line now, but the direction you are traveling in with respect to north changes across this map. To visualize what's going on with the projection process, I really recommend the first thing you look at is the shape of the lines of latitude and longitude. You can tell in this case that the mnemonic projection is sort of a cone shape because those lines of longitude are converging towards the top of the map, and the lines of latitude are curved. A cylindrical shape will give you straight latitude and longitude lines, not curved at all, and they will intersect at right angles, making them very useful for compass navigation. All right, so let's introduce the projection process with this video from Vox. Speaking of poking fun at Mercator, it's kind of like half this class, so it's a big pastime of people who do cartography. I'm gonna ask. Yeah, I think that video is really illustrative of some of the issues with projections. And the reason we're teaching you this is, of course, you're making maps. And depending on what scale you're mapping at, what use case you're going to have for your map, you're going to make different choices. And we want you to know all the different options you have available so that you can actually make the most effective maps. Any questions on that? Was that all clear? All right. If you have questions, feel free to raise your hand. So let me get my pointer back here. This is a fun article. Actually, there's a tool. I'm going to have you check that out instead. The true size. This is a fun web application where you can actually look at the true size of different features. I think we can do Montana. So let's take Montana, and let's say Montana just happened to be located further north. You know, what would the Mercator projection actually do to it? It would appear to be huge, like almost the size of Canada if it was much further north by the North Pole. And then if we put it down here in the low latitudes near the equator, you know, it looks a little bit smaller than it is actually represented at about a latitude of 45 north. So you can check this out if you'd like to, thetruesize.com. Again, I'm giving you lots of cool things to discuss at parties. Like, hey, did you know maps distort area? We've talked about this Gall-Peters projection. It's a good illustration of how we might make different choices to teach certain things, right? Especially, you know, thinking about young kids learning geography. Like, I think probably a lot of people saw this map without hearing anything about the distortions that go into creating the Mercator map. Gall-Peters tries to minimize that, but it looks kind of weird, right? It just looks kind of wrong if you've been looking at a globe or a Google map view or even a Mercator projection on the wall. So as far as I know, this is still the standard for UK schools, and Massachusetts also adopted this back in 2017. So we already talked about what is lost, right? It loses some of the shape fidelity. It loses some of that recognizable landmark character of the map to preserve areas. But it really does a good job at showing you, for instance, just how large North Africa is. So it's like the entire country, the continental United States, the conterminous United States could fit in just the Sahara Desert region. So again, we're thinking about splitting open that globe and putting it on a flat plane and conducting different transformations to do so. These dots are actually referred to as an indicatrix. So if this map had no changes in shape, all the dots would be round. But this shows you the distortion that is actually occurring, the east-west stretching towards the poles and the east-west shortening towards the equator that's required to keep all of the areas of these ellipses at the same. All right, so let's break down this projection process. The first thing you need to do is select a datum for your coordinates. We talked about WGS 84, NAD 27, and other datums last time. Those coordinates are then mathematically transformed onto a flat plane. Of course, part of this is taking the real dimensions of things and reducing their scale to fit on a map. So you might reduce the scale by a factor of 24,000 to create a USGS topographic map. And just a vocabulary term for you here, you'll see come up in various places is graticule. This is the network of lines representing latitude and longitude. So instead of referring to these as latitude, longitude grid lines, we shorten that down to graticule. If you want to add one of these to a layout in ArcGIS Pro, you need to go to the graticule options. That's what it's actually referred to as in the software. So the video did a nice job at illustrating how we can take shapes and kind of wrap them around the globe, get them as close as possible to the features of interest, and project from there. So here's an example of 3 different projection families. These are the majority of projections fall into one of these 3 families. First one is cylindrical. We can have kind of an upright cylinder here, or if we flip it on its side, 90 degrees, that would be a transverse cylindrical projection, much like universal transverse Mercator, which we talked about last time. The place on your map with 0 distortion will be exactly where that shape intersects the Earth's surface. And so for a tangent projection, that surface is just going to glance the Earth in one place. It's not going to go within the Earth at all. It's just going to have one standard line. Contrast that with a secant projection on the right side over here. You've still got that same shape, but the shape is actually within the Earth's, it's inside the Earth in some places, creating 2 standard lines. So a cartographer might choose to use a secant projection if the area being mapped is a bit more broad. And what it does is it creates lines of 0 distortion, 2 standard lines at different places on the Earth. You can imagine changing the size of that cylinder to bring those lines closer together or further apart. So if we think about the errors involved in the projection process for the cylindrical projection, on the left side, you see that 1 standard parallel because it's a tangent projection. And the further you get from that line on either side, you're going to get more and more scale expansion, meaning things actually look a little bit bigger than they are in reality. That's the exact case of the Mercator, right? Greenland looks gigantic because it's way up here on the top of the map. A secant cylindrical projection will minimize that, but you'll have an area in the center of the map where things are smaller than they should be. And then it'll be less of a problem at the poles, but it'll still be a problem with things being enlarged. Make sense, tangent, secant? All right, so the way that you would figure out whether your projection is tangent or secant is if you pull up the projection properties and you see 2 standard lines listed, you could see them listed as standard lines, or they could be referred to as standard parallels or standard meridians. Because typically you'll choose a line of latitude or longitude to be your standard line. Conic projection is really good for the middle latitudes, and that's because it's easy to get a standard line that kind of is situated at 45 degrees north. And also the distortion towards the poles is a little bit less, but the further south you go, the more dramatic the issues you're gonna see with scale expansion. So if you were making a map of, let's say, the United States, you know, a conic projection is not a bad choice because that standard line kind of runs right through the middle of the US. And then again, you can also do a tangent or a secant version of that. And then if you're mapping polar regions, you know, one of the issues with polar regions is that they're really far from the equator. And typically our focus is looking at the Earth from the perspective of the equator. So if you're really interested in the poles, you might choose an azimuthal projection with a standard point centered on one of the poles. You could also do this for other places on Earth, but the most common place you'll see this focused is in the polar latitudes. And again, a tangent projection just kind of intersects that surface in one point, whereas a secant will create one standard line. So the way that Gall-Peters works to try to do a better job with area is that it actually has 2 standard parallels, 45 degrees north and 45 degrees south, which gets rid of that major problem of having the higher latitudes appearing much larger than they are in reality. So kind of a side view, right? The intersection of that projection surface with the actual curved Earth surface here, the standard lines are the points where those 2 things intersect. So I mentioned how you can pull up parameters for projections. If you were looking at your data frame or your map, right click on it and hit properties, you can pull up this menu. And you'll find a tab. It'll be on the left side in ArcGIS Pro. This is what it used to look like in ArcMap. Tab for the coordinate system. And it'll show you what's going on with your current coordinate system. And if you select another one, it'll also show you the differences. There's also a pretty cool tool. It's this little button here, which looks like a graticule with a little bright point coming off of it. This is an interactive thing where you can tell it kind of which properties you want to preserve and what is your area of interest, and it'll actually suggest a custom projection for you. So for this example, we've got a central meridian, which is another way of saying our standard line on the map. There's only one of them, right? So the central meridian is set at negative 111, which means this is a transverse Mercator projection. We know that it has to be tangent because there's only one standard line. That standard line is going to be running north-south because it's a central meridian, right? Meridian is another word for longitude. We've got a scale factor telling us the typical distortion involved in that projection. So the scale factor indicates that it's really accurate to, basically 4 decimal places. As we mentioned last time, false eastings can be set up so that all the coordinates on your map area are positive. So this one does specify a false easting. And it's an offset by 500,000 meters in this case. We know our linear unit is a meter because it's specified right here. 1 meter is our standard unit. So what is a scale factor? If a map is 1 to 24,000, you set up your screen to display the map at 1 to 24,000. But you're using a projection with a scale factor of 0.9796. What that means is the actual scale, when you set your map to 24,000, is going to be 24,500, which will be about a 98% accuracy in terms of preserving the scale. So every single map projection has a scale factor, and map projections seek to keep that scale factor as close to 1 as possible. Already mentioned this. Azimuthal on the left, conic on the right, and cylindrical in the middle. So how do we actually choose a projection? We have to choose between 4 properties, and then we have to choose our projection surface as well. And you've got all kinds of combinations of these 2 choices. So as I mentioned earlier, a lot of it depends on where you're located on the Earth and the shape of the feature you're mapping. So for instance, if we had a long north-south feature, like let's say we wanted to map something in North Africa that it was kind of shaped like this red polygon I just drew. What we would want to do is flip this cylinder on its side, like so. Make that standard line run right through the middle of that region. So we have a good fit between our standard line, which is the area of least distortion, and the shape of the feature being mapped. I also mentioned that for Montana, right? If we put Montana kind of over here, that's Montana, just trust me. If we could situate that standard line running east-west across Montana, at that latitude, a conic projection would be a pretty good choice. There's one final thing you have to keep track of with projections. These terms will appear in the various descriptions, and they refer to the vantage points. So earlier I showed you how we can actually create a map using a mnemonic projection that shows great circle pathways as straight lines. And the way you do that is by having the illumination point originate from the center of the Earth. So it creates kind of funky looking maps, but because of the position of that projection point, right here in the center of the Earth, it actually makes the great circle pathways look straight. A stereographic projection, you can think of this as a light bulb, right? If you were putting a light bulb inside the middle of that beach ball globe that the guy in the video had, It's like put a light bulb in the very center of the Earth, you get a mnemonic projection. If you put it across the other side of the Earth, that's stereographic. And then if you put it at a theoretical infinite distance, that is orthographic. Orthographic is going to give us the most realistic looking shapes, because let's say you were rotating above the Earth in the International Space Station, looking down on the Earth. The path that light is going to take to your eyeballs is most similar to the orthographic projection path. It's approximated best by an infinite distance away from your illumination source. So kind of real world objects look most realistic with orthographic, but mnemonic and stereographic can help us preserve some unique qualities of the maps, like making those great circle paths appear straight. Too much text on this slide, but I will try to summarize for you. So these are the common terms you will see to describe projections. An equal area projection is going to preserve the area relationships all across the map. To do that, your graticule is not going to intersect at 90 degrees. It's going to distort shape. And it's a lot better if you are using larger map scales. If you're zooming in on the Earth, this is not going to look so weird, right? Projections really become a problem when you're trying to make maps of really large areas. Conformal maps, one example being Mercator. These are the ones that actually preserve the shape and angles of features. So that video mentioned how if you're driving and you want to know what is a 90-degree right turn, a conformal map is best for that. Geological maps also, and maps of topography also use conformal projections, because we want the features to have the same shape on the ground as they do on the map. So you can actually use these maps for navigation. But at smaller scales, when you're zoomed out, they do distort area quite significantly. Not a problem if you're navigating through your town. It is a problem if you're putting together a map for your social studies class. Equidistant, it is what it sounds like. It preserves area from one or a few points to all other points. Preserves distance from one or a few points to all other points. And then an azimuthal map, which is also the same term that is used for describing the shape of the surface you're projecting it onto. This preserves direction from one point to all other points. So when should we use these maps? I'll give you some examples to highlight these ideas. But you can imagine when an equal area map will be useful. Let's say you are mapping population density. You would not want to map population density using any sort of symbolization scheme on a map that was not equal area, because it could distort how you actually perceive that map. Any sort of map that a realistic appearance or navigational angles is very important should use a conformal map projection, and better to use these at larger scales. So here's an example of an equal area map, the mole wide. In just a couple minutes, I'll show you how to actually turn this on in ArcGIS Online if you want to use an equal area map projection. Here's a conic projection. I can tell because if we kind of wrap that together, it'd be like an ice cream cone. And those lines of longitude are actually intersecting at the North Pole. That's a dead giveaway for a conic projection. This is the Lambert conformal conic, which tells us that it preserves angles and shapes, and it's a conic projection family, and somebody named Lambert invented it. And then Indicatrix is really useful for visualizing the distortion that occurs for each of these map projections. All right, and then our final two kind of broad categories of applications here. Let's say you're mapping airplane range, or the range of travel times from one point to other points. You'd probably want to use an equidistant map projection centered on the point of interest. So you can actually figure out on your map how far you can travel in either direction. For sort of modern GIS, one of the tools you can run is a cost distance analysis. This is something that cartographers will use to figure out like, hey, where should I put my business? You know, how far is it from major roads? How long will it take people to travel to the storefront from, you know, high population density areas? You might use an equidistant projection to actually display those results. Navigational charts, especially of the polar latitudes, might use an azimuthal projection. Pretty uncommon that you'd actually have an application for this, but you do have a lab in which you will use an azimuthal projection to make a map of the polar regions. Couple examples here. So this map you can see is using an equidistant projection. This is a US Geological Survey earthquake warning time map. The center of this map would be the epicenter of the earthquake. Here it's along the trace of the San Andreas Fault near the Salton Trough. Anyone been to this area? Raise your hand. Kind of a wild area with a drying up lake. A lot of water use issues there. But we can tell because these are actually circles emanating outwards from the epicenter. You know, those seismic waves will be traveling at the same speed, creating those circles around that point of interest, that this is indeed a equidistant map. Here's an example where travel distances were plotted on top of a Mercator projection. So a website called Range Map shows you how far different airplanes can travel on one tank of fuel from any airport in the world. And you will notice that the vast majority of web applications and web maps use the default Mercator projection. And it creates these weird ellipses, right? There's nothing that makes it easier to fly northward than it does to make it fly southward. It's just a function of the area and distance distortions involved in the conformal projection process. So if these, you know, if this application could use a equidistant map projection, that would be, it would make those nice concentric circles. USGS maps use conformal projections because typically they are at a smaller, covering a smaller area or using a larger map scale. This is a map of the Big Island of Hawaii. And we want our coastlines to have the same sort of orientations and shapes in reality as they do on our maps. So as the video mentioned, like National Geographic and other organizations have actually adopted compromise projections, which try to do a decent job at everything, but can't do anything perfectly. When you're mapping the entire globe, you know, this is typically a good choice. Something like the Winkel triple is a good representation of the area relationships on Earth. And it also preserves like pretty recognizable shapes, so students won't be confused. And here's that indicatrix showing that areas are a little bit enlarged towards the poles and a little bit smaller towards the center of the map, but it's not nearly to the same extent as the Mercator projection. Some comics, there's this comic called XKCD, and I think the person who writes the comic took a lot of cartography courses or does GIS, because there's so many comics about map projections. But it's almost like a personal preference thing. Like Mercator, whatever, default. I'll just use this. Everyone else does it. Some other ones. Dymaxion, you like this projection if you like Isaac Asimov, XML, and shoes with toes. You know, kind of a nerdy map projection, etc. So you can check out these comics on the slides. And then maybe you're feeling this way, like, can he shut up about the Galt Peters already? Goodness. All right, we're going to do a quick exercise in ArcGIS Online. If you would like to follow along, you can feel free to do that. And one thing you'll notice about ArcGIS Online is that it is actually quite difficult to change your map projection. So I'm just signing in here. So let's open up a blank map. And we can recognize now when we zoom out on this map that you are indeed looking at the Mercator projection. It's actually slightly different than the Mercator projection you will find on your desktop software. It's called the Web Mercator, which is the standard version of the Mercator projection used in like web design websites as the default base map. Again, as we mentioned, it's useful when you're zoomed way into Bozeman, Montana, and you're just kind of navigating around this region. You know, it's not going to be a huge deal. Like the tobacco roots are not going to be enlarged relative to the gravelly range in any sort of significant way. But if you were wanting to create a map, let's say for your story maps, remember your proposals are due tonight. I had a few people ask me what that entails. It's just those 5 questions. Type them up, turn them into the assignment submission folder. But yeah, zooming way out, it becomes kind of problematic to use this base map. For example, we might be mapping population density. So if we browse layers, let's choose from Living Atlas. There's this cool new data set called World Population Density, and this particular organization, it's a collaborative effort with researchers at different universities and remote sensing agencies. Let's see if it actually loads. But what this data set does is it actually uses the various census geographies around the world and tries to create a standardized representation of population data. For whatever reason, it is not showing for me. Let's take that one away, actually. So North American population density, just to emphasize why this might be a problem, right? Let's say someone, for whatever reason, wanted to kind of recreate the population density values. If you're using this base map and you had a map scale down at the bottom somewhere, you could measure a box, say set it up to be 1,000 kilometers by 1,000 kilometers, and you could actually use the map legend to try to figure out how many people are in that area. If you took that same size box and put it up here, as we've learned, the shapes of features on the map are highly distorted, right? So if you tried to do that same thing, used a box, try to figure out how many people live in that area, if you're looking at different areas of the map, it's going to be telling you different things, and it's not going to be an accurate representation of the data. So if you were mapping population density, you would want to choose a equal area base map. This map is a product of the World Pop effort. The reason that this map was created is because it gets beyond the census polygon geometries. You know, we've dealt a little bit with things like the census tracts, the zip codes, the counties. This effort actually takes those data sets and uses satellite imagery to try to figure out where within the polygons people exactly live. So using things like visible lighting at night, land use, land cover data sets, we get a more accurate representation of where people actually live. Pretty stark contrast, you know, between the eastern half of the US and the western half of the US, right? Mexico is, you know, much more densely populated than you might assume. And holy cow, there's like nobody in northern Canada. But also, that's a much smaller area than is represented on this map. So how do you change the base map? The only way to do it in ArcGIS Online. Yeah, sorry, question. How do I change the? Yeah, so if you want to change projections in ArcGIS Online, you either need to create your own custom base map on desktop and upload that to ArcGIS Online. So on desktop, you could create, you could have the state or country outlines. You could project them in a certain projection system, upload them to ArcGIS Online, and then use them as your base map. Or you can find an existing base map to use to change your projection. The base map gallery is over here on the left side. And all of these base maps are going to be using the Mercator, Web Mercator projection. But there are a few that exist that use different projections. So I just hit that, that plus button to add a new base map. And I'm selecting Living Atlas. Let's actually search for equal area. Sorry, this is a little bit different search functionality. So I want to go back to the Layers tab and just hit Add Browse Layers instead of clicking on that from the base maps pane. And you can find a tile layer here from a cartographer named John Nelson, actually the chief of cartography at Esri, has a whole YouTube channel and everything. And if you add that base map, it should appear in your list of base maps. All right, first thing I'm going to do is remove the actual thematic layer I added. So we don't have any projections that need to happen. And then in Living Atlas, search for equal area. And then because we don't have any layers that are being used on the map, it should show up. And for some reason, it's really hard to read. But there we go. We've got an equal area base map in ArcGIS Online. And then you should be able to add things like population density back in. Well, and that actually reverted it back to Mercator. So bottom line is it's kind of difficult to do this in ArcGIS Online. One of the reasons why desktop is still relevant, right? It's difficult to do, but there is a way to use a different base map in ArcGIS Online. Oh, and that's because the North American population density is actually a base map. So if I remove this, it'll go back to my other projection. All right, thanks everyone. I'll see you next week. Have a good time in lab. Hey there.
I had a quick question about the story map.